Okay, welcome to those of you on the online. I see more people are online today than last time. Very good. Okay, we'll give it a minute. Oh, no, we're past time. Okay, great. Well, first of all, thanks to all of you who did email and respond for assignment 1. So if you haven't done it, do it today. I'm not going to be super strict about it, but I would say do it. If you don't do it, then I might assign you to a topic that you're not excited about. So that won't be a good thing. Okay, so today's lecture, actually, what I want to do is just go through potential projects. And my goal here is really to give you some ideas of things that I think could be potential topics. Not necessarily, again, dictating these, but just some ideas to think about. And hopefully it'll spark some ideas as you talk with your teammates. And I know some of you did not suggest teammates to work with. That's perfectly fine. That just means that I will assign the teams as I mentioned last time. Okay, so let's get started. Are there any questions so far? Okay, no. Everyone has access to Canvas. Everyone who's here. You got the videos and you can access Slack and so on. Okay. If not, just send me a message. And those of you on the online, just you can send a chat message if you have any questions or concerns. So I want to first talk about water. Water is, of course, extremely important for all of us who live here. So we need to be concerned about it, but it's also a huge problem around the world, as we all know, right? So it's a big problem. And I'm going to think about water from two perspectives. One, of course, from an optics perspective, obviously, but I'm going to think about it from two areas where I think we can contribute. One is water pasteurization, and the other one is water desalination. And we'll try to understand what the differences are and what needs to get done. So first, solar water pasteurization. What does that mean? Pasteurization, as we all know, when milk, when we go to the supermarket and buy milk, it has to be pasteurized because when it comes out of the cow or sheep or whatever, it has bacteria which can potentially be harmful to humans. So getting rid of that is really what that means. Now, this is a big problem. Something like 1 in 6 people on this planet do not have access to clean water. So it's a big problem, but it's also a huge opportunity, one way to think about it. There are many rich countries actually who are water starved. As we know, we live in one, right? But also countries like Israel. I think more than half the water of Israel comes from desalination. And Saudi Arabia, if you think about it, and all those countries there. I've been to both those countries and I can tell you water is expensive and they have to have very complicated systems to deal with. Half of the hospital beds in the world are filled with people suffering from water-related diseases. I mean, this is something we don't see in the US, but it's very common around the world. And of course, vast majority of childhood mortality is related to contaminated water. So very, very important problems to deal with. So what are the solutions? What can we do about it? So pasteurization essentially means you need to get rid of the microbes. And there's a very specific temperature that you need to get to so you can denature the proteins that make the microbes active. So as we all know from COVID, to denature the proteins that basically make up the RNA of the virus, you have to get to some temperature, right? Or you have to use UV or something like that, which we'll talk about. Same kind of thing applies here, but for water, it turns out to be 149 degrees Fahrenheit or 65 degrees Celsius. So the key observation here is you do not need to boil the water. Now, why is that a key observation? Because boiling water involves a phase transition, right? You're going from liquid to a gas. That's very expensive energetically. You need to throw in huge amounts of energy to make that phase transition happen. And that is an important observation because for pasteurization, you don't need to expend that energy. You only need to get to that. It's an important observation. Definition of pasteurization, of course, the use of moderate heat to kill diseased microbes. Doesn't have to be heat, can be UV as well. We'll talk briefly about that. In the example, so it depends on the material. So in the case of milk, it's 71 degrees Celsius for 15 seconds. So that's highly efficient, I suppose. And then the studies have shown that 65 Celsius for water is kind of the ideal temperature. You can get rid of vast majority of bacteria. So from what we know so far, oops. So I want to stop here for a second. From what we know so far, can you identify any problems with it? And I'll give you about 30 seconds to talk to your neighbors. So from what I've shown so far, what are the problems with water pasteurization that you can think about? For those of you online, feel free to chat with with the group. Let's take a quick. I mean, you should see some problems, right? You have to do something, otherwise, so you have to spend some energy, some money, whatever. You are welcome to talk to them. You don't have to, but if you want. Any thoughts? Anything that I mean, there has to be problems, right? I'll ask you. If you have, I mean, don't mean to put you on the spot. If you have something, please feel free to share. Yeah, that's a great point. What's your name? CJ mentioned that it's not only the microbes that are important, but also things like dirt or taste bad or whatever, right? You don't want to drink salty water, even though it's not going to kill you. That's a very important point. I completely agree. I wasn't thinking about that either. So, do you have something? Someone raised their hand. Yeah. Oh, yeah.
So that you need everyone to have heat properly.
Yeah.
Yeah, I'm talking today, we would not get it up to 65.
Yeah, yeah. Over is okay. You can, yeah. So, so you raised a couple of important points. So let's summarize. One is that thermal mass of water is very high. That means you need a lot of energy to actually bring it from room temperature or wherever it is to that temperature. And you raised a second point, which is really what I was coming to, is you want to get to 65 and you can go over. You can go a little bit over to be conservative. You don't need to go to 100. I mean, you can if you want, right? But that's overkill. But the real common sense question is, how do you know when it's 65? It's not obvious, right? It's not going to boil. The water looks the same. You look at it, you can't tell. You can't touch it with your finger. You can't tell it's 65. How do you know? That is a problem that I didn't think about. But of course, it's a very practical problem, right? If you're out hiking and you want to drink your water, that is something you need to know. And of course, the way people deal with it is just to boil it, which is overkill. So that was a very interesting and important problem that we don't think about, that someone actually thought about and solved. A very simple solution. I'm going to show you that. Basically, a temperature indicator that indicates 65 degrees. Simple idea, right? Extremely simple idea, very, very fast. So I like these simple ideas because it's easy to understand and gives an idea of how you can apply creative thinking to solve problems. So it is quite simple, but basically they came up with the wax that is engineered so that it will melt at 65. So let's look at a quick video. And there was a company that commercialized it. So it wasn't a nonprofit. It was a company that commercialized it. And don't worry about the volume. I'll just walk you through it. So they call it Whoppy, water pasteurization indicator. It's basically in a little glass tube. you can see the wax is solid on the top in white. And once it reaches the temperature, so it shows, let's see, you can see it became a liquid, fell down, so it melted, and that transition happened. Of course, this wax has lower thermal mass than water, right? But it tells you when you reach that temperature. Very simple idea. Now, what other technologies exist? So one of the first things you have to do, again, think of these as, if there's something interesting in the chat, feel free to tell me, yeah? But, yeah.
Many areas now water are forward, energy water is expensive.
Yes, very good. Yeah. Yeah. Thanks, Nathan. Yeah, I think those are all very valid. Great. So one of the things I want you to do for your first presentation is to understand the landscape of solutions. And we're just taking this as an example, and we'll try to do a few of these, but just to give you a flavor for what I want you to think about. We're only going to spend a few minutes, but you have to spend a little more time. So what other technologies exist? Of course, it's a very simple problem. There are simple solutions. You can use, of course, use a solar cooker, as shown on the left here, right? You can just heat it up. But again, you need to have the Whoppy to know the temperature and things like that. Are you looking for me? Oh. Sure. The second technology, of course, is much simpler. It's like just a greenhouse. So it's a container, kind of like the enclosed solar cooker. So I'll just quickly play this video also. They call it an aquapack. So they talk about the problem, but we all know this. But essentially, they have a Whoppy installed in this package, so you know when the temperature is reached. You fill it up, you leave it out in the sun, acts like a greenhouse, and you can see what happens to the Whoppy. Before it looks orange, after it's colorless, and then it can be reused, of course, right? When it comes back to room temperature, it solidifies. And the last part is very important. They can utilize materials that are locally available, which is an interesting approach that this company used in order to widely disseminate the technology. I don't know exactly how they make money, but was their approach. Then I'll show you the simplest possible solution is to use PET bottles. It exists all over the world. You leave it out for several hours in the sun, and it's not only the temperature, but also the UV rays, which will kill the bacteria. Of course, these are problematic. I'm sure you can imagine problems as well, right? Because you don't know, in this example, of course, you don't have the Whoppy, so you don't know if it's clean. You don't know if the UV was sufficient, and you still have the taste issues and so on. By the way, Kata, keep a note of people trying to get in as well. I just noticed someone was late. Okay, now let's move on to the next. Oops, why is this? There we go. Sorry, I don't know. Okay, good. Now let's move on to the next idea in water, which is desalination. Now again, keep ourselves in check. Pasteurization is drinkable water, and desalination means, and that means, like CJ pointed out, it cannot be from the ocean because you still need to get rid of the salinity, the brine, right? So in the case of the ocean, so for example, in Israel or in Saudi Arabia or in parts of California, like in Southern California, when you pump in the seawater, you have to do desalination. In other words, you have to separate the salt from the water so you can make it drinkable. Of course, that's not the only thing you have to do. You still have to get rid of the microbes and all that stuff because the ocean is not perfect, right? So anyway, yeah, so let's talk about that too. Of course, desalination is what happens naturally, right? This is a hydrologic cycle, which we are all very familiar with. This is natural desalination, one way to think about it. You have water from the ocean evaporates over time, huge surface area, right? Over the day, as the sun heats it up, it becomes water vapor, forms clouds. With wind, the clouds move onto land. And when they hit the Wasatch Front, we get our snow and water, and that gets the fresh water. So that is a desalination process. As the water evaporated, salt is left behind, oceans remain salty, right? And the fundamental reason is simple. The boiling point, the phase transition of water happens at a temperature much lower than that of the salts, right? We want to emulate this artificially. We want to speed it up because we can't rely on rain, particularly because of climate change and so on, as we all very well know. So the most common technology is reverse osmosis. It's pretty simple. Let's start with the left-hand side, which is conventional osmosis. If you take a container of pure water and separate it from salty water with a filter, which is shown here, what you will see is that the filter has pores which allow water molecules to pass, but it will not allow salt molecules to pass. So that's just the size of the holes. So water molecules can freely pass from left to right, sorry, right to left. Salt molecules cannot pass the other way. This is traditional osmosis. If you leave it like this, the second law of thermodynamics dictates that both sides should reach the same concentration. The left-hand side will dilute, so its concentration goes down. The right-hand side will get more concentrated, right? Because it's losing the water. And when I say concentration, I'm referring to the concentration of the salt. And it will reach an equilibrium, right? There's a pressure equilibrium. This is completely dictated by the second law of thermodynamics, which we will see again. Here, we're talking about the second law of thermodynamics in the context of chemical potentials, because you have a chemical concentration on one side that is trying to equilibrate with chemical concentration on the other side. In the future, we'll talk about the second law of thermodynamics in the perspective of optics. Now, of course, some of you probably know that the second law of thermodynamics is the reason why we all exist, right? Life exists, and the universe is expanding and so on, all of this, and the fact that time flows in one direction and so on. So it has very, very big implications, obviously. In any case, so I'm going way off topic. So let's come back to reverse osmosis. What we want to do, of course, is the opposite, right? We want to get pure water, not dilute, not make it more saline. So you have to do some work on the system. So the second law of thermodynamics is important here because second law of thermodynamics means if you do nothing, naturally, entropy will increase, which in this context, that means the concentration of salt in the water on the left-hand side will decrease, but you are going to lose water on the right-hand side. So you're not getting clean water out. Now, in order to get clean water out, you have to work against the second law of thermodynamics. This is a common theme we will see again and again. That means you need to put some energy into the system to counter the effect of the increase of entropy or the second law of thermodynamics. A very, very fundamental thing. You have a system. If you don't do anything, it will equilibrate. If you want it to do something, you have to put some energy into the system. And what does that mean? And we'll see many examples. In this example, what does it mean? You put pressure on the left-hand side to push the salty water through the membrane. Now, what will happen? The membrane will block the salt molecules, but will allow the water to pass through. So on the right-hand side, now you'll get clean water. On the left-hand side, you leave the salt. Okay, pretty common sense, but you have to do work. This is the reason, it's the reason why reverse osmosis is very expensive. And only rich countries in the world today can afford to do it. Israel, Saudi Arabia, California. Very expensive. I'm hoping some of you will work on technologies which will try to solve this, because this is critical to the future of, I would say, of humanity in a sense. Now, so of course, that's a key problem, right? Energy required to push water through the membrane, but it could be produced by photovoltaics. I'm going to look at some examples. Can anyone see any other problems with it? So energy and cost is one. Anything else? And let's maybe take 10 seconds, talk. You can talk, but maybe all of you also talk. Or maybe let's take 10 seconds and talk about it. Short break. Yeah, go ahead. You have to speak louder. I can't hear you. Yes. Waterfalls or. Mm-hmm. Yes. Yeah. 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 You can think about there are lots of ideas along this. That's really good. Yeah. So Amartya mentioned that you can come up with some other ways to create that pressure using, let's say, a heat engine, like you heat up a gas, for instance, that expands it, pushes it down, and so on. Any other interesting? Actually, I was looking for problems, so that's a solution. So that's good. But any problems someone noticed? I know you. I see you guys are discussing. So, anything interesting? Exactly. That was exactly what I was looking for. This is a huge problem, right? Think about it this way: you're pumping seawater on the left-hand side, and you're pumping it out, right? Millions of gallons. You're leaving salt here, and the salt is built up on the filter. At some point, those holes will fill up, right? And what does that mean? That means you're going to have to put even more energy to push the water through because the holes are less efficient. So over time, if you don't do anything to the filter, you're going to exponentially increase the amount of energy you have to push through it. So of course, the solution is to replace the filter. And that sucks, right? Because the filters, that's a cost. And you might have to replace it very often. And that's another expense. 3M makes a lot of money selling those kinds of filters. So it's a huge business to come up with all kinds of clever filters like that. I see what you mean. So you can keep the salt far kind of circulating in the system further away from the filter because it's dissolved. Yes, that is correct. Yes. Yeah, I have to think about it, but let's keep going in the interest of time. Good. But in any case, I want you to, all of you, to think when you do your literature search. But the key lesson here is think about problems that are, of course, obvious problems, but also things that are not so obvious. Also, there might be some interesting solutions you can come up with. Oops, let's clear this. Okay, so photovoltaics is the primary energy source. Of course, this is an obvious solution, right? You don't if energy. So this is useful for many cases. Of course, it can be portable, right? Or disaster relief. So if you had a hurricane, if you can have something that can be deployed because the clean water may not be available right after. So right after Hurricane Katrina, you saw all these people in camps in the big dome, right? And they needed water. How do you you had to truck in the water? But if you had a way to generate the water locally, that would be a good problem. So here I'm going to show you one solution that is from a lab. This is from about 8 years ago. So it's not super, new, but it gives you an idea of where a particular problem has been solved. I'm going to play the video and talk about it first. Then we'll come back to that question. Actually, let's zoom in here for a second. So the system looks like this. So first of all, you need a water storage tank. You have to keep the water somewhere. That can be big, right? So that's a problem. Desalination system is there. Those are the filters. So water is pumped through the filters. It's in there. There are many stages, and we'll see that in a second. And there are photovoltaic panels with the tracking system to track the sun, and there's control electronics. Now I'm going to play the video, and then I'll walk you through it. This was a project at MIT where, so first of all, the top left is the system they had on the roof, where you can see the panel is following the sun, and you can see the little tank there is getting filled up with clean water. And there's another tank in the back which had salt water. This is the solar insolation over time. So from the morning, very low, keeps going up, going up, going up. Remember, there's a pump that is pressing the water through the filter. Yeah. One important thing that I think we learn in electrical engineering as undergraduate, and some of you in mechanical engineering probably know better than us, is that for a motor to work, and we all know who drive, we all know this, for a motor to work efficiently, you want it to go at a fixed speed, right? Now, I think many of you know this, right? On the efficiency of your car in the highway is much better than on the city streets because you're not stopping and accelerating and decelerating. The exact same thing happens here. And this is a problem because, as you saw, sunlight input is highly variable, right? It can go to, even in the middle of the day, if the cloud comes in, it drops dramatically. So the current going to your motor can drop dramatically. That's really bad, right? It will drive the efficiency of motor down. So what they did here, they came up with an optimal controls problem, some circuits with a battery, such that you can maintain a fixed pressure on the motor. Made it much more efficient over the time of the day. Again, a problem we don't think about. It's not so obvious. It's an important problem, nevertheless, that they solved. So in the interest of time, we won't, maybe we can come back to this, but I want you to think about, can you think of ways you can use optics to help here? We haven't talked about it, so I'm going to skip this for a second. And if you can think of ways to improve it. I'll show you one other approach. Are there any questions before I? Yeah, you can read it out. Yeah, that's a good question. I don't recall, but I think there's a link on our class website. And if you're interested, send me a message, but I know those folks, so I can find out. But you can see the aquarium, how big it was producing. So it was that aquarium, which I think is like a 10-gallon one. I can't remember, but it got filled twice a day. So it had about 20 gallons. So this is another example, also from another group, Evelyn Wang's group at MIT, who developed a slightly different approach to improve the efficiency of the water desalination. And it's useful to think about this as well. So, and this is more recent. This is from last summer, actually. So let's look at how it's done. So first of all, starting from the left-hand side, sunlight comes in. You have a transparent insulator, so you're trying to keep the heat in, kind of like the greenhouse. You have a heat absorber, a black body to absorb the heat, so you can engineer it to absorb as much heat of the photons from sunlight as possible. Then you have something interesting. So you have a tank at the bottom, which has the water that you input into the system. And then you have a wicking material that they designed. So Evelyn's group, Evelyn's a material scientist, and her group develops all kinds of very clever materials. So this was an example of some material they developed. So this wicking material brings the water up, and the heat absorber transfers the heat. It's just a heat transfer problem into the water, and then the water evaporates, and the fresh water condenses here. Now, what was clever is that they designed this material such that the heat, so when the water evaporates from liquid to gas, it is absorbing some of the heat, right? It is increasing its kinetic energy. So it's absorbing the heat from this side. So this means that this surface gets cold, and the water vapor will then condense on the cold surface, and it'll flow down into something that you can get here. So the idea was that they utilize this heat loss from, usually this heat loss from evaporation is lost. They designed essentially not just one stage, there are multiple stages like that to take advantage of that to increase the efficiency of the system. And it's a nice paper if you're interested. And I think I have a link to it as well. That's a photo of the system, so you can kind of get a sense of the scale as well. By the way, Boston is not a very sunny place, so it's kind of interesting that it still worked. So you can see the panels up here, the clean water here, and they're just weighing this stuff. Sorry, this is the dirty water with the wicking material up here, and the clean water goes down. So lots of interesting things to explore. So this was kind of like a materials, but optics related. So optics comes in here because you need to design the materials to absorb as much of sunlight as possible, which is photons, right? Optics. At the same time, you want the water to be wicked up. And as the water evaporates, you want the heat to be re-radiated out to the next stages, so it can be collected again for further evaporation of the water, heating of the water as well. Oops. Okay, now I want to talk a little bit about, let's call it less technologically savvy or older technologies. These are important because the vast majority of water that's generated is not for humans. Vast majority of desalinated water is used for agriculture, which, as you can imagine, or for livestock, right? So most of that, the way it happens is something called salinity gradient solar ponds. Many of you probably know about it. They're pretty simple. You basically have a large pond where you can see as the water heats up, as Amartya was pointing out, it can dissolve more of the salt, and then it gets heavy and it sinks to the bottom. So the bottom of the pond has high salt content, hot brine. And as you go up, there's this gradient layer of temperature and also salinity. As you go up and up, it becomes less salt content because it's colder. Okay, and of course it circulates. So it's not a passive system, right? It's dynamic, it's moving around and so on. But this gives you sufficient salinity gradient that you can now start pumping from different parts. So for instance, now if you take the water from the top part of the pond that has low salt content and it's colder, now you can use that to run what is, in this example, you can use it, of course, for agriculture, whatever. But in this example, you can see it's actually running a heat engine to generate electricity. So slightly different application, but you can imagine it can also be used for water. So let me point out here, what's happening is that the cold water, that's the cold part of the heat engine, okay? That allows, it cools whatever is getting in touch with it. And on this side, we have the hot part of the heat engine, okay? It allows whatever the working fluid is to evaporate. And in this example, the working fluid can be air or can be water, it can be something else. But the fluid here passes through, like you can see over here, goes through a turbine. So the liquid, after it condenses on the top, the cold part will flow down, run a turbine to generate electricity, go down to the hot part, becomes gas, goes up again to the cold part, condenses, becomes liquid, goes down, runs the turbine, becomes gas again and goes down. This is called a heat engine or a heat cycle. Okay, so it's a way to use the cold side and the hot side together to create energy. And then we will see this again and again. In fact, a solar cell is doing the exact same thing, a completely different manifestation. So it's good to think about this from an abstract perspective. Now let's look at some of these details here. So the denser, saltier water heats up at the bottom. The middle layer acts as an insulator. The top layer remains cool, produces low-grade heat, less than 100 degrees Celsius, thermal energy. It's useful for heating. In some places, you can actually pump it into the homes and so on. It can also be used for electricity production. The efficiency is relatively low, 10 to 15%, but it's low tech, it's inexpensive. It can absorb all kinds of sunlight, whether it's cloudy or not, you can still get some of the light. Right? It doesn't need to be perfect cloudless days. Oops. You can also have a flat plate collector, very similar ideas to before, but it's more deliberate, where you have these collectors that essentially heat up, and then you can use those surfaces to essentially heat up the water, which might be flowing underneath it. In this example, you can see it's flowing through here. These lines right there. And then it goes through those stages that you can see on the right-hand side, what's labeled silk cloth, that's just a filter. So you can see the water is flowing through those filters, getting rid of some of the impurities that someone was mentioning before. So here again, you have two tanks. You have a brine collection tank, which is the outlet of the water, and then there's a freshwater tank, which is the outlet actually. The brine collection tank is just so let's make sure we understand this first of all. So so the water comes in here, and it's heated up because of those the plate collectors right there. So it becomes, it's a gas, it's water vapor, and it condenses on this cold surface, and then it flows as water into these little gutters you can see here, and it's collected down here. Oh, yeah, maybe let me go back. It's actually collected into here. And the brine, which condenses on the top here, and it can also go through the filter, but it also goes down into the connected tank here. In any case, yeah, you can design it many ways, but this particular one is something. Okay, so here there are a couple of other things to think about. What kind of materials should we design to absorb the light? Very similar to the one from Evelyn Wang's group. Do you want to put anti-reflection coatings? In other words, you don't want to lose much light out of the system, just reflect it out. You want to absorb everything as much as possible. Again, you want the ideal devices like a black hole, but you want everything to go in. You can also have better light collection of optics and things like that, which of course is not included. There's no optics here, it's just a plate, right? So many of you have probably seen these on the roofs of buildings. It's very popular in China and in Europe, where you have these flat plate collectors for hot water for homes. You can, of course, also use parabolic trough collectors. So it's a parabola. So as you can see, it's a one-dimensional parabola. And it's one-dimensional because as the sun moves during the day, you can tilt the parabola to follow it. If it's two-dimensional, tilting gets a bit more expensive. And if it's one-dimensional, you form a line focus, and you can run the water through the line focus in a tube. And as the water heats up, if it is water, then it can be collected. The water vapor, of course, leaves the salt behind, and the water vapor is collected as pure water. Of course, you can also use this for generating electricity, which is mostly what these things are used for. And they are, of course, more expensive systems. By the way, the scale, let me just point out the scale of the system is quite remarkable. Here you can see a person to give you a scale. So they can be quite giant. Now, there are other types of these salinity gradient ponds, which I won't spend a lot of time on, but just so we are aware of them. You can have a simple greenhouse kind of effect where you just have water in the pond at the bottom here. And it's because it's an enclosed greenhouse, it heats up, and as it evaporates, it hits the glass cover, which is colder, and the water condenses and comes down into the freshwater drain that you can see on the right-hand side here. So there are lots and lots of ways to do this. Now, at this point, I want to take a minute or so and try to do an example problem. Again, the goal of doing an example problem, there are two goals, actually. So first of all, it's to take a break so you're not bored. to refresh your brain, because everybody's attention span is spot. Not great. Second, I want you to think in approximate terms, being able to do back of the envelope calculations, and also think from dimensional terms. So think about units and things like that. So refresh our undergraduate engineering classes. Okay, so let's read the problem. And feel free to discuss, by the way. Let's say the energy required to evaporate 1 kilogram of water at 30 degrees Celsius is 2.4 times 10 to the 6 joules. So that's the amount of energy you need to put into a system to completely go from liquid to the gas state, okay? 1 kilogram of water. If we assume that the solar insolation is 250 watts per meter squared, which is the amount of power per unit area that your system is receiving. Imagine let's visualize this. Imagine a container of water, 1 kilogram, you put it out in sun, you're getting 250 watts, and let's say it's 1 meter squared for the sake of argument, okay? Question is, how much water will be, I'm asking, can be produced per unit area per unit time? What does that mean? How much water is evaporated out of here? And let's say you collected it. Let's assume 100% efficiency. Okay, now I'll let you, feel free to discuss with your neighbors. If you want, you can just work it out yourself too. But I want you to just think about it, you know? And those of you online, also I would say, work out. Yes, Jared, good question. How do you know when the water is done? In this question, I didn't specify it, but just assume, I'm assuming that it is evaporated up, because that's my first information I've given you, is the energy to evaporate 1 kilogram of water. So how much water means, what is the weight of water that's evaporated? You're welcome to talk. Right? This is just a simple example, but you know, you get the idea. I want you to be able to think in scales, you know, kind of approximate things. So the way I would approach this is I would start at, say, 250. Oops. Hold on, Jared. 250 watts per meter squared, right? That's the amount of energy I have to work with. Now, what does that mean? That's equal to 250 joules per second per meter squared. That means every second I'm getting 250 joules for a meter square of area. And I said, let's assume meter square because I'm asking for per unit area output. Now, that's the rate at which the energy is coming into the system. Now, the rate at which the evaporation happens, I need to divide that, right? So this becomes 2.4 times 10 to the 6 joules per kilogram, right? The rate at the bottom is the energy I need to put in for every kilogram of water. Rate at the top is the amount of energy I'm getting into the system per unit time per unit area. Now, one thing you can check to check your logic, this is a very important thing I want you to think about, is check the units, right? The joules cancel out. So the units of whatever I'm calculating here should be kilograms go to the numerator, seconds remain in the denominator, meters squared remains in the denominator. So that will be the units of what I'm calculating. And that makes sense. So I'm looking for kilograms of water per unit time, per unit area. So it's a good sanity check to make sure I didn't make any logical mistake. Okay. The answer itself is not terribly important, but let's work it out anyway. So what's this? 250 divided by, I'm going to do back of the envelope. 40 times 10 to the 4. So I'm going to say this is approximately 10 to the minus 4 kilograms per second per meter squared, or 0.1 grams per second per meter squared. Is that okay? Not a lot of water. Maybe a little, 0.1 grams is what, 100 milligrams? Yeah, maybe a little container. Maybe a cup. I don't know much the dimensions to ounces. Okay, so again, it's a very simple, let's see. There was a question in chat. No, Jared, okay, good. Okay, got it. Very good. So again, just to reiterate, there are two things I want you to get out of the very simple example. One is the idea of back of the envelope calculations. It's okay to make approximations because there will be lots of things that we don't know. You won't know the efficiency of your system properly. So you have to make some approximation. But whenever you do your projects, it's good to make approximations, but try to make a reason for why you did that approximation. Okay, I wouldn't do it arbitrarily. I'd just be aware of it. And the second thing is the idea of sanity checking with the units. Okay, which is extremely useful in all many cases. Okay, let's keep going. Yeah, so one thing we did do in this example was we assumed it was 100% efficient, which of course it never is. Sorry. In this case, the typical efficiency is about 30 to 40% in that particular case. So the material selection is important. You can still do lots of improvements on the system design as well. We already talked about this, the solar cell greenhouse combination. It's very similar to what we just talked about, but you can actually have a greenhouse inside with plants growing and so on. This actually turns out to be very important in temperate climates, especially if you want to grow things in the winter. And it's very common, for instance, in the Scandinavian countries, where they combine these things, the water generation, heating, and particularly small scale farms. I won't go through the details here, but one of the very important challenges which we talked about last time is the problem of corrosion. Salt is, of course, extremely corrosive, right? For those of you who might know, if you have a, you might have gone to a beach house or something, you can see all the sidings of the house is essentially corroded. It has to be replaced much more often because of the salt in the air. Same thing happens here. So remember, you're collecting salt or very salty water that'll corrode the system. This is one of the big problems in desalination systems, including the filters and so on. You have to keep replacing the filters, not only the filters, the pipes themselves. How do you deal with this? This is, by the way, a huge problem. And if you Google, there is a, I should put a link to it, actually. There is the Bureau of Land Reclamation, ELR. They are the ones, the federal agency that deals with water. So they deal with allocation of water. Of course, they're becoming very important with the drought here. Now, they have to deal with the huge pipelines that transport water. And in the case of desalination systems, they're transporting salty water. They have to know when these pipelines are going to fail. They have to predict because they're giant, right? They're like 10-meter diameter pipelines. You can drive a car through it, right? And they're expensive. And if you're passing water through it all the time, and water's not perfectly pure, it will deposit and so on, it will start corrode away. And to replace these things, you have to turn off the water, you have to replace it's a really expensive proposition, so you have to plan ahead. How do you know when it's going to fail? This is a very important problem, which is being solved with optics. In fact, what I was going to say was that there's a prize, you know, I think you're all familiar with X Prize and so on. There's a bunch of these prizes, and one of the prizes is offered by the Bureau of Land Reclamation to develop a system to inspect pipelines and be able to predict their failure way in advance. And some of the examples they demonstrate or they cite on the description has to do with optics. You know, different kinds of cameras, robotic crawlers that go through the pipeline that can look and try to identify the cracks or corrosion and so on. Very, very important problem. Actually, an interesting project topic for some of you. Still in the theme of water, there's the idea of humidification, dehumidification, which of course here we are familiar with. And if you go to the East Coast, the problem is the opposite. The humidity is too high, you need to dehumidify. And an air conditioner does this, for instance, right? So you can do this with solar energy as well. Again, it's a question of, it's a heat engine, it's a system where you input energy. So in this example, dry air goes in, it's heated by the solar collector, those plates we saw in the last 2 slides ago. That hot air now goes into a humidifier or a diffusion tower where the water is mixed in with the hot air. The hot water evaporates, goes along with the hot air. The saltier water or brine goes out, and the warm humid air containing the water vapor goes into the other side, which is the dehumidifier, and condenses on the cold side. And in this example, then you get the air out, which is a little bit humidified. You get the condensate out, which is the clean water. And you can also pump in cold seawater in, which is preheated because of that system in the dehumidifier. Remember, as it condenses, it's going to preheat the water, and then the preheated seawater can go into the dehumidifier. Sorry, to the left-hand side, the humidifier. And it's a system, as you can see. The details are not super important. I mean, you can work it out yourself. But to me, what's important is to understand this concept of the heat engine. There's a hot area, there's a cold area, and this difference allows you to get some work done. It allows you to work against the second law of thermodynamics, okay? Against nature, I suppose. So just a quick example, air is the working fluid. In this case, a kilogram of air can carry about half a kilogram of water vapor, so it's very, very efficient at about 80 degrees Celsius. So that's a good way to do humidification. It's relatively inexpensive, but it's still, I mean, somewhat expensive, I suppose. So it's comparable to reverse osmosis, particularly because of the efficiency. The systems themselves are relatively inexpensive. So just to summarize, we talked about 2 different approaches for desalination. One is a direct approach where you use solar to simply heat up the water, create the distillate, right? It can be very inexpensive, very simple systems, or you can use concentrators and all kinds of clever optics. Or you can have an indirect system where you use the sunlight to produce energy and then use the energy to do the work, whether it's reverse osmosis or whatever. Okay, so we thought about 2 different systems. When you think about topics, and I know some of you are interested in desalination, this might be a good place to start. How you do a literature search to understand what's out there.